Okay, so now we're going to do Chapter 10 review. And let's do number 1. So number 1, I'm going to look at number 1, and I'm going to look inside of the square root. It's a fraction. It looks a little bit blurry, but maybe not. It's 400 divided by 5, so 400 over 5. And I ask myself, will 5 go into 400? And if you're not sure, you can do it on the side. Will 5 go into 400? 5 will go into 4. No, 5 will go into 48 times, and there's a 0. So now, instead of 400 over 5, I've got radical 80. Then ask yourself, is there any perfect squares within radical 80? And we can break it down. Well, I know 4 times 2 is 8, and I know 4 is a perfect square. But I don't want 8, I want 80, so I'm going to make that 20. Okay, so now, so far I've got 2 as a whole number, but can I break radical 20 down into a perfect square? I've got radical 4 and radical 5. Okay, what's the square root of 4? We just did that, which is 2. We bring this 2 down to meet it, because now we have 2 numbers together, and it means multiplication, but we still have radical 5. What's 2 times 2? 4 radical 5. So that's your answer. You might have had a different way of doing it, maybe a little quicker, but that one I just broke it down step by step and kept going until I couldn't go anymore. Okay, this one should be a give me. What's the square root of 144? 12. Easy, in your head, no problem. Okay, number 3, I look inside of my radical or square root symbol, and can I simplify that fraction in any way? And I cannot. So at the top I have radical 10, at the bottom I have radical 81. Okay, so what's the square root of 81? Is 9, so that's my denominator. And then I have radical 10 at the top. Is there any perfect square within radical 10? 1 and 10, 2 and 5. There's not. So there's my answer choice for number 3. Okay, number 4. Let me go ahead and move this down just a hair. Come on, move. There we go. Okay, now I got number 4. And the first thing you want to do, again, is look to see if you can simplify the fraction. Will 2 go into 126? Well, will 2 go into 12? Yes, 6 times. Will 2 go into 6? Yes, 3 times. It's still under the square root. Is there a perfect square within 90 or 63? And I know that 9 times 7 is 63. Is a 9 a perfect square? It is. Square root of 9 is 3. Radical 7. 7 is a prime number. There's no perfect square within that. So here's my answer for number 4. Number 5, I've got the square root of 300 over 3. Ask yourself, within this radical, can I simplify that fraction? Will 3 go into 300? And it will. 3 will go into 3 once, and there's 2 zeros. What's the square root of 100? The square root of 100 is 10. So there's my answer for number 5. Number 6. Okay, can I simplify this in any way? No, but I can break it down into a perfect square. I know that 7 and 4 makes 28. I know that 4 is a perfect square root. And 7. What's the square root of 4? 2 radical 7. And that's my answer for number 6. Okay, number 7. I have a radical and a number, so I can't simplify that. I have a radical in the denominator, so I'm going to multiply both top and bottom by radical 21 because I want to clear that radical in the denominator. So when I take the square root of 21 times the square root of 21, I'm just going to get 21 back. I don't even have to multiply it because what I get back is what's inside the house. At the top I have 4 radical 21. Okay, I look at the 4 and the 21, and I look to see if that can be simplified, and it cannot, so therefore I am finished. Okay, so back to number 7 real quick. Can you cancel the 21 and the radical 21? You cannot, because radicals can only go with radicals and numbers go with numbers. So this is my answer. I can't simplify it any further. Okay, the next one, again, I have a number on top, a radical at the bottom. I can't do anything to simplify it, so I need to clear the radical on the bottom. I'm going to rationalize the denominator. Okay, so 10 times 10 is 100. What's the square root of 100? And that's 10. That's what goes at the bottom of my denominator. I've got 4 radical 10. Then I look and see I have numbers now. Can the 4 and the 10 be simplified? Well, 2 times 2 is 4, so 2 will go into 4 2 times. 2 will go into 10 5 times. So now I've got 2 radical 10 over 5. And I look at the radical 10 and say, can that be simplified anymore? And it cannot. There's nothing that's a perfect square within radical 10, so there's my answer for number 8. Alright, number 9. First of all, let's go ahead and multiply. Numbers go with numbers. So let's multiply this -2 times 4, or -2 times 2, which is -4. Then I multiply radicals with radicals. 2 times 22 is 44, and I keep the x. Okay, then let's look and see, can 44 be broken down into a perfect square? I'm going to keep the -4, radical 4 times radical 11, and then I still have the radical x. So I have -4, what's the square root of 4, which is 2, and now it becomes multiplied by 2. And I have radical 11, and I'm going to go ahead and write the x inside with the same radical, because I can't do anything with either of those. -4 times 2 is -8, radical 11 x. And that is my answer for number 9. Okay, let's do the second half now. Okay, this next problem, number 10, is a distributive property. Remember, numbers multiply with numbers and radicals with radicals. So I've got a 9 times a radical 16. So they don't multiply together. I'm just going to write 9 radical 16. Then I have a 9 times 7. 9 times 7 is 63, and it's positive. Okay, within radical 6, is there a perfect square? There's not. I can't put the 9 and the 63 together because the 9 is connected to that radical 6. So I am all done. And this is my answer for number 10. Okay, now just like we did previously on the other page, let's go ahead and simplify the fraction inside the radical first if we can. 3 will go into 6 one time, 3 will go into 3 one time, 3 will go into 6 2 times. Okay, it's still a square root. Can we break that down? We've done this a few times already. To 4 radical 3, and you get 2 radical 3. And that is my answer for number 11. Okay, maybe you did it another way. I'm going to show you the other way, but either way, I just want you to show me how you get it because there's more than one way. I can take the square root of 36, and then at the bottom I have the square root of 3. What's the square root of 36? Is 6, and then I have the square root of 3. But therefore I have to rationalize the denominator, so I'm going to multiply top and bottom by square root of 3. Square root of 3. 3 times 3 is 9. What's the square root of 9? Which is 3. And at the top I have 6 radical 3. Okay, but one more step for this one. One more step for this one. I could cross cancel 3 will go into 3 once, and 3 will go into 6 twice. So now I have 2 radical 3. And it's the same answer that we got down here, except this one was a little bit shorter, but we got the same thing. Alright, let's do number 12. Okay, remember, radicals multiply with radicals, numbers with numbers. So, I am going to multiply. Okay, I went ahead and erased the work for 10 and 11 because I want to focus in now on 12. Okay, so now remember, numbers multiply with numbers, radicals with radicals. So there's only one number here, which is 2. So I'm going to keep it. And then I'm going to multiply 6 times 21, because that's a radical. And that's going to be 126. And I'm going to keep the x in here. Okay, then I asked myself, is there a perfect square within 126? And I wasn't sure, so I went ahead and did my hockey stick method. And I did my prime factorization. So I start with 2. Will 2 go into 126? It will, because it's even. It's going to be 6 and 3. Will 2 go into 63? No. Will 3 go into 63? Yes. 3 will go into 2 times, and 1, 21. Will 3 go into 21? And it does. And then will 3 go into 7? No. 5? No. 7 will. Okay, so now I have my prime factorization over here, and I look at the numbers. Is there any numbers that multiply together to give me a perfect square? Look at 3 times 3. Oh, look. They have the square root of 9. That's a perfect square. Then I have 7 times 2. That's 14. Okay, so now I keep the 2. What is the square root of 9? The square root of 9 is 3. I'm going to multiply it with 2. I'm going to keep the radical 14. So 3 times 2 is 6, radical 14. And I look at 14. Can it be simplified? Is there a radical within there? 1 and 14, 2 and 7? No. So there's my answer, 6 radical 14. So if you have to, you may have to use a hockey stick or prime factorization to find perfect squares. Okay, now let's go to number 13. We're almost done. This again is a distributive property. Radicals multiply with radicals, numbers with numbers. Well, I have a 14 and a radical 10. Can't put it together. I have a 14 and a 10. Let's multiply that. I get 140. Within the square root of 10, is there a perfect square? There's not. I cannot separate the 14 from radical 10, so I just have the answer 14 radical 10 plus 140. Alright, I'm going to stop and erase a little bit so we can focus in on the next one. Alright, now let's focus in on number 14. And I have a quantity inside of the denominator. They're radicals, so I need to clear the radicals by multiplying, and we called it the conjugate. So I'm going to multiply the bottom by 5, the opposite of what's there, minus radical 2. What I do the bottom, I have to do the top. Radical 5 minus radical 2. And what I did was I just made a difference of squares. So that means I'm going to go back, and I am going to take the square of both sides here. So I'm going to end up with 5 and a 2, and it's always minus. So 5 minus 2 is 3. So that's what's on my denominator. On the top, I have a multiplication problem. I have 4 times radical 5, which is just 4 radical 5. And then I have a 4 times radical 2, and I just have a 4 radical 2. And I'm always going to have the sign that's in there is going to determine the sign, and it's minus, because a positive and a negative is a negative. Okay, so then I look at that, and I looked at the numbers, the 4 and the 3, and see if I can do anything to simplify it, and I cannot. So right here is my answer choice. Okay, the next one we have it looks like two quantities that are both radicals that I need to multiply together, or maybe you recognize it as a special case, and I hope that you do, but if you don't, then we can do it the longer way. Okay, so we'll do it the long way and then we'll talk about the short way, the shortcut method. Okay, so it's going to be radical 15 times radical 15, which is radical 225. Then we're going to multiply with the outer. So this was the first, the outer. So 15 times 2 is 30. And it's a positive times a negative is a negative. And this is the inner. So 15 times 2 is 30. And positive is a positive. And then the last. 2 times 2 is 4. And it's positive and a negative is a negative. Hopefully you see that the radical 30s cancel because one's positive, one's negative. Square root of 225 is 15. The square root of 4 is 2. And it is a negative. So 15 minus 2 is 13. So I wrote 12, didn't I? It's 13. So 15 times 2 is 13, so my answer is 13. Okay, if you remember the shortcut method, I'm going to go ahead and just erase my arrows so I can show you what I can do by remembering that it's a difference of squares that is created here. You square the first term and you square the last term and you get 15, and it's always minus 2, and that gives you 13. Because I recognize it was a difference of terms. So find the difference of terms. You square the first term, you square the last term, and then it's always subtraction, so it's 13. Okay, a couple more. Okay, number 16. We have parentheses and it's squared. So that means I'm going to write my quantity twice. And we are going to multiply it using the FOIL method first. And then again, there's a shortcut for this also. And we'll talk about that in a minute. It's perfect square trinomial, so maybe you remember that. Alright, so it's going to be multiplying radical 3 and radical 3, which is radical 9. Radical 3 and an 8 is positive 8 radical 3. Then an 8 and a radical 3 again, because we're multiplying it. And then 8 times 8 is positive 64. Okay, so now what's the square root of 9? 3. I'm going to combine the radical 3's together. I have 8 plus 8. 8 plus 8 is 16 radical 3. And then it's going to be plus 64. Okay, numbers go with numbers and radicals go with radicals. So now I have a 3 and a 64. That gives me a total of 67. I keep the 16 radical 3 because that's the only term of radical 3's I have. And so therefore that's my answer choice. 67 plus 16 radical 3. Okay, so now if you remember, and I'm going to go ahead and erase this, if you remember our perfect square trinomial, what you do is you square the first term. So that's going to be 3. I'm going to square the last term, which is 64. It's always positive here. Then I take 8 times radical 3. I'm going to move this 3 a little bit. You say 8 times radical 3 is 8 radical 3, and then you take that middle term and you multiply it by 2. So now I have 3 plus 16 radical 3 plus 64. And that's what I had down here, except I just did a little bit shorter method. And then we're adding together the 64 and the 3, which is 67 plus 16 radical 3. So both ways I get it. If you forget the different perfect square trinomial, just do it the FOIL method. Alright, now we're getting to triangles. Okay, so the direction says determine whether the given lengths can be sides of a right triangle. And remember, we're going to use Pythagorean's theorem. A squared plus b squared equals c squared, where c is always your longest side. Okay, so let's do number 17. And we've got 7 squared plus 11 squared. Does that equal 12 squared? And so you're just going to go ahead and do the math. And you don't need a calculator for this, because you should know 7 times 7 is 49. 11 times 11, 121. 12 times 12 is 144. And then I'm going to add 49 plus 21, so that's 10. 4, 5, 6, 7. I have 170. Is 170 equal to 44? It is not, so my answer to number 17 is no, it is not a right triangle. Okay, number 18. I'm going to do the same thing. We're going to see if they're equal. If they are, then we have a right triangle. If not, then we don't. So 18, again using Pythagorean theorem. So we've got, and I know I don't say that right, but it's close enough. 30 squared plus 40 squared is equal to 50 squared. Remember, the longest side, the longest number, the biggest number is your C. So let's see, I've got 30 times 30. Well, 3 times 3 is 9, and there's 2 zeros. 40 times 40. 4 times 4 is 16, and there's 2 zeros. 5 times 5 is 25, or 50 times 50 is 25. Well, 50 times 50 is 5 times 5 is 25, and there's 2 zeros. Okay, you got the idea. Let's add these together. 900 plus 1600. We got 2 zeros. This is 5. Carry the 1. 2500. Is 2500 equal to 2500? And it is. So number 18 is a yes. Alright, number 19. It says find the length of the missing side of the nearest tenths. So we've got, again, we'll use the Pythagorean's theorem. So it's 4 squared plus 7 squared equal to c squared. So now we got 4 times 4, 16. 7 times 7, 49 is equal to c squared. So now we're going to add 49 and 16. So I've got 15, carry the 1, 4, 5, 6. I got 65. And then I've got c squared. And then you're going to take the square root of both sides. And so I've got c is equal to the square root of 65. Since I'm not going to give you a calculator, we're just going to leave it. We don't need to worry about the nearest tenths. We're just going to leave it as a radical. And if you get the correct radical, even out in simplest form, I'll keep it. So it's c is equal to radical 65, and that's good enough for me. Alright, number 20, last one. Using the same theorem, 5 squared plus 12 squared is equal to c squared. So 5 times 5 is 25. 12 times 12 is 144 is equal to c squared. Let's add 25 with 44. So we got 9, 6, 1, and that is c squared. Take the square root of both sides. So if I take the square root of c squared, I get c. And over here, 169 is 13. You should know that one. That one's pretty common. And that is my answer for number 20. Okay, I hope you watch this because you're going to see real similar questions on the test.